Hello there. In this video, we are going to talk about functions and function notation. First thing is, what is a function? What does it mean to be a function? And what does it mean to be one-to-one? Now, a function is a set of ordered pairs. A lot of times we think of those in terms of a graph, but it can just be a list of ordered pairs where every input, every x value leads to exactly one output or y value. So I won't see the same x value going to two or being paired with two different y values. Okay, so no x values paired with two different y values. One-to-one flips everything. So a function is one-to-one if every y value leads to exactly one x value. So there's no y values that will be paired with two different x values. And we abbreviate this 1-1 because we don't like writing out one-to-one over and over again. So if you see either one, they mean the exact same thing. Okay, so let's do an example with this. So here I have two relations. So they're just a list of ordered pairs. And I want to figure out if they're one-to-one and if they are a function. So I'm going to be checking both of those things. So let's look at that first one in A. I'm looking at all my x values and I don't see any repeats. I've got an x value of 1, 2, 4, and 5. None of the x values are repeated and being paired with different y values. So this is a function. To figure out if it's a relation, now I'm going to focus on the y values. And I do see that the two middle terms have the same y value twice. I have that 3 there. Once it's paired with 2, once it is paired with 4. And so this is not one-to-one because of that. Now, I know this is a little tricky and it can be hard to keep straight, but we are going to look at a couple of tests that make it a lot easier when you're looking at the graph to figure this out. Now let's look at that at part B. So slightly different values here. And this time, if I look at the x's, I do see the x value of 1 paired with two different numbers. So I have the 0.12 and the 0.13. And the reason we don't like this in a function, or why we care about whether something is a function, is I don't want to plug in a value and have the possibility of getting more than one y value out of that. I want, when I'm dealing with a function, I want every x value to have a unique y value that it's paired with. So this one doesn't, so it is not a function. Now, if I focus on the y values this time, I don't see any repeats. I've got 2, 3, 5, and 6. None of them are repeated and paired with a different value. So this one is one-to-one, but not a function. Okay, so the vertical line test and the horizontal line test will help us with this to figure it out if I'm looking at the graph. And even on those last examples, if I wanted to, I could have plotted all those points and used this test to determine whether it was a function or one-to-one. So the vertical line test is testing to see if something's a function. And basically, if I can draw a line through the graph, anywhere on that graph, where it hits the graph twice or more than once, then it's not a function. So I can see 3 examples here. The one on the left, anywhere that I try and draw a vertical line through this thing, it only intersects the graph once. That makes it a function. With the other 2, well, you can see I am able to draw many lines where each one of these, the vertical line intersects twice or more. And so that makes them not a function. The horizontal line test works the same way, only this tells me whether a function is one-to-one. So if I can draw a horizontal line through a graph and hit it more than once, then it's not going to be one-to-one. So for instance, my function on the left here, I have this nice curvy wave. I can definitely draw a horizontal line through that intersects the graph more than once. So that is not one-to-one, even though it is a function. And the middle one, well, I can't draw any horizontal lines through that intersect more than once. So that one is not one-to-one. The last one, I can draw horizontal lines that intersect that ellipse or oval shape. And so that's not a function and it's not one-to-one. Okay, so that's how those tests work, and you can do it with a relation that is just a bunch of points or a continuous curve like these examples here. Now, in this unit, we're going to be reviewing or looking at a lot of common functions. We'll oftentimes call this like your toolkit, or you just want to be familiar with these parent functions And later in this unit, we're going to learn how you can use these to come up with the graphs of different functions that are very similar or maybe just located in a different place. So I'm not going to spend a lot of time on these, but you do want to become familiar with these over the course of this unit and just have a general idea of what their shapes look like. First one is the constant function. It is just a horizontal line. It's f of x equals just a number. The identity function is a line that's at a 45-degree angle. F of x equals x. And we have the absolute value function, which is this nice V shape. Quadratic function, which gives me this U shape that we call a parabola. Cubic function gives me that nice S shape there. That's x cubed. And then four more, the reciprocal function, 1 over x, gives me this shape. And so I have two kind of curves in the first and third quadrant. Reciprocal function, square root function, and cube root function are all the ones, the basic functions that we want to be familiar with their shape. And if you go through all of these functions are functions. They pass the vertical line test. They do not all pass the horizontal line test. For instance, that reciprocal function, you can definitely draw a line through there that goes intersects it twice. So that one is not one-to-one, but it is a function. Okay, so getting into function notation, you might have heard me use that phrase f of x. Well, that is this notation f parentheses x here. It's read f of x, and it can be used in place of y. It gives us a little more information because if I'm using that notation, it is implied that I'm dealing with a function, so it passed the vertical line test. It also names the function using a letter, so here it's f. You might see a g of x or h of x, anything like that. You can use any letter for the name of the function. And what it does is it tells me what the input is as well when I have it written as f of x. Something else we want to be able to work with, and we'll look at examples of all this, is the difference quotient. Now, this is using calculus, so we want to be familiar with it as we get ready for taking a calculus class, because many of you will be. And so the difference quotient is where I take the function and I evaluate it at x plus h, which are both variables, where h is not 0, minus f of x divided by h. Okay, so this is using calculus. We won't get into what the number means in the end or function that we get from it, but you do want to be able to set up and simplify this expression. So we'll be practicing that in this class. Okay, so let's do an example with this. So here I have the function f of x equals 2x plus 5. So really it's the same thing as saying y equals 2x plus 5. We're just using this function notation here. And first we're asked to evaluate it at x equals 6, and then we're going to find the difference quotient for the function. So if I'm evaluating it at x equals 6, that means I'm replacing all the x's in the function notation and in the function itself. I'm replacing all the x's with 6. So it looks like this. F of 6 is equal to 2 times 6 plus 5, which if I simplify that gives me 17. So I can write this as f of 6 equals 17, or I could write it as the ordered pair 6, 17. So the part in parentheses next to my f is my x value. What I got from plugging it in is the y value. So those mean the same thing. There's two ways of writing the same thing. Okay. Second thing we want to be able to do with this is find the difference quotient. So remember, the difference quotient is f of x plus h minus f of x all over h. So I'm taking this function, 2x plus 5, and for f of x plus h, I'm going to replace x with x plus h, and then minus the original function divided by h. So I end up with 2 times the quantity x plus h, in parentheses, plus 5, minus the original function, 2x plus 5, all divided by h. So that's the setup. It takes a little getting used to this notation, okay? So if you're feeling a little overwhelmed, don't worry about it. We'll practice and we'll get the hang of it. The only thing left to do now is to just simplify this. And you should be able to simplify this quite a bit every time you do it. So keep that in mind. If you're finding, gosh, nothing is canceling or simplifying at all, then check to make sure that you've evaluated everything correctly. So I'm going to start by distributing to get rid of all the parentheses. So the 2 gets distributed and the negative gets distributed. So I end up with 2x plus 2h plus 5 minus 2x minus 5. So I can see I got a 2x minus 2x. Those will cancel out. I have a 5 minus 5. Okay, this is the kind of thing you want to see when you're doing the difference quotient, is at least a little bit of cancellation. So the only thing that doesn't cancel on the top is 2h. And I end up with 2h over h. The h's reduce, and I get just 2. So the difference quotient for this particular function is 2. Okay, so there's some examples underneath this video to help you practice this a little bit more.